Welcome to the FLAC. Let's dive into some overall review for solutions, molarity, concentrations in chemistry by solving problems like this one, and this one, and this one, and this very useful one, a parts per million review, and a solubility rules review. You'll learn everything you should know how to do in this solutions review. When it comes to solutions, alcohol is technically a solution. But all kidding aside here, remember that the addictive and dangerous component of alcohol, ethanol, is responsible for a lot of families breaking apart and auto vehicle accidents and many other negative and horrible things. However, we're going to use it as an application to chemistry. If we know that whiskey is typically about 40% ethanol by volume, that's the 80 proof part, that roughly equates to a 7 molar solution of ethanol. We want to know how many grams of ethanol are in a 7 molar concentrated drink of whiskey if we had 240 milliliters of said drink. Since this is a practice video, go ahead and pause the video here to see if you can figure out this problem before I show you the answer. The setup you'll need to follow is right here, just for your reference. Ready? Go! All right, let's see if you got your answer correct. As you can see, there's quite a lot of ethanol in just one glass of whiskey. Here's your next practice problem. If we wanted to prepare a 0.9% solution of a saline IV drip bag, which is the typical solution that a hospital would use, how many grams of salt, NaCl, would need to be dissolved in 1 liter of water? Go ahead and pause the video here to see if you can solve the question before I show you the answer. Ready, go! Alright, so in order to make a 0.154 molar solution of saline for your IV drip bag, you would need to mass out 9 grams of salt on a scale and dissolve that in a liter of water. Now if we carry on practice number 2 into practice number 3, let's assume that you are still the doctor in the hospital and there's an emergency at the hospital and there's only 1 bag of IV solution prepared by a horrible intern that never took chemistry and had no idea about solutions. Let's assume that the physiological saline, that salt IV drip solution, has to be at the 0.154 moles per liter, that 0.9%, in order for it to not burn like hellfire in your veins. But unfortunately, this very uneducated intern made 1 liter of IV solution at 0.454 molar. Ouch! And you have no other option but to dilute this 1 IV bag that's super concentrated to save the patient. Luckily, you know the M1V1 equals M2V2 equation. Go ahead and see if you can solve this problem before I show you how to do it. Ready? Save the patient! Now don't be fooled by this V2 calculation. What you've got is the total volume. What we want to know is how much water we need to add to the already concentrated solution that the horrible intern created. So really what we need to do is subtract out the volume we started with, the 1 liter, from the total amount we should have at the end. So 2.948 liters minus the initial 1 liter that we started with would give us the amount of water we need to add, which is 1.948 liters of water we would need to add to the solution that the intern had already created. This practice question hits home on a personal level here. When you need to make weed killer to literally destroy all those pesky evil weeds that come up in your yard, especially to avoid HOA violations, you often have to dilute a stock concentration that you'd buy at Home Depot or some hardware store and put it into this cool little pressurized pumpy sprayy thingy. Typically, when we dilute that toxin in the pumpy sprayy pressurized spray tank, there's 10 liters that we're trying to fill in that spray tank. If we needed 3.5 molar solution in that full spray tank, how many milliliters of the 8 molar starting stock concentration of ground clear should we use? Go ahead and pause the video here and see if you can apply M1V1 equals M2V2 to save us from our HOA violations. Go! If we were to measure out 4,375 milliliters of our concentrated weed killer and mix that with the difference from 10 liters, which would be 5.625 liters of water, we would end up with our 3.5 molar weed killer solution. Here's a blast from the past practice question. If we want to know what the concentration is in parts per million, ppm, of TCE, that's trichloroethylene, if 1.3 milligrams was found in 2,500 kilograms of Tucson, Arizona's soil from the groundwater. By the way, this is a real thing. There was a TCE underground water contamination in Tucson, Arizona. Then let's revert back to our ppm mathematical setup to solve this question. Go ahead and pause the video here and give it a shot. So the concentration found in Tucson soil then is 5.2 times 10 to the negative 10 parts per million of TCE. Here's another blast from the past, talking about Flint, Michigan here. The lead and water problem in Flint could have been avoided if they would have simply added sodium phosphate to the water supply. That's this guy right here. If they would have done that, the lead could have been brought out of the solution as a precipitate. But how do I know that that would be the case? We need to revert back to our solubility rules, of course. So looking at our solubility rules, we can look at our products and see what would be soluble in solution, i.e. aqueous, and what would be a precipitate, i.e. a solid, S. In this case, sodium would be a charged cation, and it would be surrounded by water molecules in solution. So we know that Na, in this case, would be AQ, in solution. How about the lead phosphate? Let's look at our solubility rules for lead and for phosphate. We see lead here, and we see phosphate here. In the cases of lead up here in the soluble compound area, they would only be insoluble if it was paired with chlorine, bromine, iodine, or sulfate, in which case it's not paired with any of those. It's paired with phosphate. So let's check out the phosphate here. Phosphate is an intrinsically insoluble compound, except if it's paired with an always soluble ion. Since none of those always soluble ions are lead, then we must know that since PO4, our phosphate, is an insoluble compound, that would make this lead phosphate insoluble as well, i.e. it would be our precipitate, our solid. Now that we know that our lead phosphate is our solid precipitate, and sodium would still be in solution as aqueous, let's figure out how many grams of this solid precipitate would come out of the solution if we had 350 milliliters of 0.00045 molar lead solution here reacted with the sodium phosphate here. Given my hint of the setup down here, see if you can figure out this practice question on your own first before I give you the answer. Ready, go! Let's check your work. So as you can see, if we would have taken 350 milliliters of 0.00045 molar lead solution and reacted it with our sodium phosphate, we would have yielded 0.0426 grams of lead phosphate as a precipitate dropping out of the solution, meaning that the Flint, Michigan residents wouldn't be drinking it in their solution. In this lesson, we practiced the different layouts of stoichiometry using concentrations and molarities. Remember that a solution is created by dissolving a solute in a solvent. And if that solution is too concentrated, i.e. it has a high molarity, a high amount of moles per liter, or perhaps it has a high concentration in parts per million or parts per billion, ppm or ppb. We can use a dilution of M1V1 equals M2V2 by adding more solvent, i.e. water, to that solution to dilute it. If a solute does end up dissolving in a solvent, then we say it is soluble in that solvent. If it does not dissolve, or if it crashes out as a precipitate from mixing two different solutions together, then we say it is insoluble, or a solid. If something remains in solution, we also represent that as AQ, or aqueous. And most of the time when we're dealing with precipitates, we're going to be looking at double replacement reactions. Some of the most common setups you'll see in stoichiometry are as follows. If this is something that's confusing to you, I encourage you to please write down these setups, as they'll likely be what you encounter over and over and over again in chemistry. Please give this video a quacks up, and I hope that this review will certainly help you. Wishing you a very quacky ducky day.
Because I love my duck.